In modern science, astrophysics typically treats macroscopic spacetime geometry and microscopic quantum phenomena as two entirely distinct and separate domains. The bulk spacetime geometry and the properties of the event horizon are determined strictly by the Einstein field equations. But the thermal emission from a black hole, Hawking radiation, relies on a different framework, semi-classical quantum field theory operating on a fixed curved background. This thermodynamic view was established by deriving the mechanisms of particle creation right at the horizon. Because of this, geometry and thermodynamics are generally treated as mathematically independent structures. This suggests that black hole thermality is an isolated quantum exception, rather than a standard result of macroscopic rules. We need to determine if macroscopic geometry alone can dictate thermodynamic scaling without requiring the input of quantum field theory. We start with a radiative boundary closure. This is a condition that restricts the allowed combinations of luminosity, temperature, and radius at the surface of an emitter. In astrophysics, this classical closure usually applies to ordinary stellar photospheres, where it physically dictates the exact point of atmospheric decoupling. We will apply this exact standard radiative closure directly to a Schwarzschild event horizon. This approach does not construct a new metric solution, and it does not replace the semi-classical Hawking calculation. If successful, this shows that Hawking thermality is an admissible limit of standard radiative structures required by the geometry of the spacetime. We begin with a dimensionless boundary relation. It contains only macroscopic boundary data and standard constants. On the left, we isolate the macroscopic variables: luminosity, temperature, and radius. These variables are the foundational bedrock of all standard blackbody mechanics. Mathematically, this relation converts into its standard operational form, L equals 4 pi r squared sigma t to the fourth. This is the definitive macroscopic closure for any quasi-spherical thermal emitter. It acts as a rigid constraint, physically restricting the allowable combinations of heat, size, and light output. This generic boundary structure is universally applicable, setting the baseline requirement before we shift into the relativistic limit. Now we move to the relativistic limit. We shift the definition of radius from a physical plasma boundary to a boundary dictated entirely by geometry. For a non-rotating black hole, that geometric constraint is the Schwarzschild radius. We substitute the Schwarzschild radius into the spatial variable of the boundary closure. Squaring the geometric term expands the constants. Condensing the terms, the limit becomes L equals 16 pi sigma g squared m squared over c to the fourth times t to the fourth. The arbitrary physical radius has been eliminated. In its place is the mass of the spacetime. This classical substitution locks luminosity, mass, and temperature together. It shows that event horizons enforce a specific thermodynamic scaling. Solving for temperature yields the admissible radiative branch. Temperature is proportional to luminosity to the 1/4 times mass to the negative 1/2. This relationship maps onto a coordinate system using luminosity, mass, and temperature. The Stefan-Boltzmann law creates a surface of every theoretically possible thermal state. The Schwarzschild geometry acts as a mathematical constraint slicing through this space. Their intersection creates a single path. This result is purely macroscopic. No microscopic emission mechanism or semi-classical particle creation is assumed to draw this curve. A black hole cannot exist off this specific path. Out of all possible thermodynamic states, the Schwarzschild horizon selects this singular radiative branch. The geometry of the spacetime forces the thermodynamics onto this track, independently of how the radiation is produced. We can now compare this to the findings of quantum field theory. The classical derivation does not provide the exact numerical prefactor for the Hawking temperature. It also does not derive the rate at which the black hole evaporates. For those details, we look to the semi-classical evaporation scaling law. Quantum field theory shows that luminosity scales inversely with the square of the mass. We can now see what happens when we apply this quantum evaporation rate to the classically mandated admissible branch. We return to the geometric scaling relation. We substitute the semi-classical evaporation term into the luminosity variable. Multiplying the exponents reduces it to mass to the negative 1/2. Combining the mass variables reveals the final rule. Temperature is proportional to mass to the -1. This is the Hawking mass scaling. It is structurally compatible with the classical radiative closure. The Schwarzschild horizon is a limiting realization of a standard radiative boundary. Hawking thermality occupies the specific branch mandated by the geometry of the spacetime.